non-zero sums of n squares in the field. So I will call them Sn of f. So these are all the non-zero sums of squares in the field. I need a notation for all the non-zero sums of squares in the fields, so I call them S of f. And unfortunately I also need a notation for all the sums of squares in f including 0. So I know they are almost the same, but it's annoying to write statements with only one of the two notations. And I need the definition of Pythagoras number. So the Pythagoras number of a field is the smallest integer n, positive integer n, such that any sum of squares in the field f is a sum of n squares. So I will denote it by P of f, and can write it as the infimum of the integers such that the sums of squares are sums of n squares. So of course there is no reason a priori why one such integer should exist. So that's why I use the infimum. So in case this set is empty, we say that the Pythagoras number is infinite. So this is called the Pythagoras number. Good, so you can see it's a definition involving sums of squares, so somehow it should remind you a bit of the Pythagoras theorems for the triangles, right? So you sum two squares and you obtain the squares of the other side of the triangle. So here as well we are summing squares and wondering, can we remove some squares? Can a sum of two squares be a square? Can a sum of three squares be the sum of two squares, and so on? I will need another invariant for the field f, which is called the level, and it's denoted by S of f from the German word for level, and it's the minimum integer n, such that -1 is a sum of n squares. Again, there is no reason why this should exist. So in that case, I say that the level is infinite. So let's write it explicitly. So this is called the level. Okay. Let me also mention that if the field f has infinite level, so if -1 is not a sum of squares, we say that f is real. Or formally real. I will just say real. Good, so you can see, for example, the field of the real numbers, -1 is not a sum of squares, of course. So the real numbers are a real field, so it's a good name. But okay, let me give you some examples to make sure that you are following me. And I would also like you to comvince you that computing the Pythagoras number of a field is it's easy to ask what the Pythagoras number of a field is, but it's much more difficult to compute it. But okay, let's start from the very basic case. So, what is the simplest field that we know? The field with two elements, for example. So, so there are only 0 and 1, which are squares. So of course the Pythagoras number of f2 is 1, and the level as well. And actually, this is true for any field f with characteristic 2. So you see why? So if I take an arbitrary sum of squares, in characteristic 2 the double products disappear. So this is actually square root. Okay, so we will mostly focus on characteristic not 2. So if f is a field of characteristic non 2, one easy observation that we can make is that for any element I have this equality. So it's just a little trick, and this is nice because it allows us to say that if -1 is a square, is a sum of squares, so if the level is finite, by just definition of level, if -1 is a sum of squares, so you know that this is also a sum of squares, so any element will be a sum of squares, right? So if the level is finite, then f is all made of sum of squares, and moreover, the level is by definition the smallest length as a sum of square of -1. So any element will actually be a sum of the level plus 1 squared, right? So we have this inequality, and of course, being the level the minimum length as a sum of squares of -1, then of course we also have that the Pythagoras number is at least the level of the field. So, okay, there are still two possibilities in this case, but it's usually relatively easy to work with this with no real fields. So I will also mostly focus on real fields, so on fields with infinite level, or equivalently where -1 is not a sum of squares. Okay, so let's see, for example, if Q is an odd power of an odd prime, then the level of FQ, the field with Q element, can be 1 or 2, so it's always finite, and it's 1 or 2, it's easy to check. And the Pythagoras number is always 2, so you can see that both of these cases in this situation already apply. But as I was saying, I'm not going to spend much time on the non-real field, because they are what can happen is very limited. Let's go on. So the Pythagoras number of the real number, what is it? 4? No, the Pythagoras number, so take any sum of squares, it's a positive element, right? In the real numbers, sums of squares are positive. So since it's positive, I can take the square root. It will be again a real number, so any sum of squares is a square. But I know why you said 4, because you were thinking about cube, the rational numbers. So you might know the, okay, this is 4. You might know it from the Lagrange's 4 squares theorem, which says that any integer is a sum of 4 squares of integers. Actually, showing it for q is easier. So it can be proven with Euler's 4 squares formula. So which is a formula which allows you to write explicitly the product of two sums of 4 squares as a sum of 4 squares. But okay, it's easier than for Z, but it's still not trivial, and it requires some formula which was found by Euler, so it's not as old as Pythagoras. And okay, what's the next kind of fields that we can analyze? The number fields. So I mean a finite extension of Q. So the Pythagoras number of a number field is at most 4, but this is much more complicated than to show than for Q. So this is also known as Hilbert, Landau, Siegel theorem. So it was formulated by Hilbert in 1899, but he just formulated it. So he said, okay, it's true, but the proof is difficult, and he never published it. So then Landau proved the statement for quadratic extensions of Q, and only after more than 20 years, Siegel managed to prove it for an arbitrary number field. So you already see that, okay, the first examples are trivial, but already with very basic fields, it really takes some clever people to obtain results. So the next question might be, what happens if I add a variable? So I take the fraction fields of polynomials over Q. So Landau already in the beginning of the 20th century showed that it was at most 8, but they strongly suspected it was much lower, and in fact it is at most 5. But this was proven by Bourget only in the 70s, and the proof is really elaborated. It requires some trick and a lot of notions, and it's very technical also. And yeah, it's really getting complicated. I would like to give you another example, but for which I need to give the definition. So, okay, probably you know what an algebraic function field in one variable is, but let's write it. So, given a field K, we call an algebraic function field algebraic generated algebraic field extension of transcendence degree 1. So a way to write it is that this is field extension, transcendental field extension F over K, for which there exists an element F such that F over Kx is finite, is of finite degree. But yeah, okay. Finally generated transcendence degree 1 field extension. So what happens for a function, an algebraic function fielding one variable over a number field? So, well, we know that it is at most 6. So let me just write algebraic function fielding one variable. That's for short. And this was proven by Pope in 1991, even though it's not published yet. And here things really get complicated. So in order to show this, we need a local global principle. For the only proof we have for now is based on a local global principle involving elaborated techniques with cohomology, and it's really a complicated argument. So things are really becoming very complicated. And moreover, for all these fields, so for any number field, we can compute explicitly if it's 4 or 3, or if kt is 5, 4, and so on. But for an arbitrary function field, so basically it's just a finite extension of this field. But already for this kind of fields, we don't know anymore how to compute it explicitly, and we don't even know if this bound is optimal. So it's actually conjecture that it's at most 5, but we don't have proof yet. Okay, let me give you the last examples before reaching Bézout domains. So you know the field of formal power series or Lorentz series. So it's proven that this Pythagoras number is 1, and more surprisingly, maybe, it's 1 even if we iterate the formal power series. Okay. I think this was proven by Choi, Dai, Lam, Resnick in 1982. No. Okay, I don't know who wrote. It's easy. I agree. It's much easier than the other ones. I don't know who stated first, but let's just say. So basically, the field is Hissensilian. So computing the Pythagoras number reduces to computing it on the residue field. So we can go back to the real numbers, but I'm not really interested in this. I'm interested in function fields over this. So if we take a function, algebraic function fielding one variable over such a field, then we have a bound, which is 3, an upper bound. And okay, for any algebraic function field in one variable f over one n. Okay, so and this was proven by Becher, Grimm, and Van Geel only in 2014. So this is also quite a complicated proof. So it involves a local global principle obtained with cohomology techniques, and it also involves non-trivial part of algebraic geometry, namely a resolution of singularities of curves. So things really get complicated even for fields that are not too bad. So anyway, I hope by now I convinced you that already computing an upper bound for the Pythagoras number is a task that is ambitious enough, and certainly for a colloquium of 1 hour. So I would like to talk a bit more about this. So in the proof of this statement, as I was saying, it involves a local global principle which allows us to check at completions and other techniques. But if one looks at the proof, one can observe that at certain point, from the techniques that are used in this paper, it turns out that there exists a subring H of F having some properties. So I won't list all of them now, but so first of all, F is the fraction field of such a subring. Second, H is a Bézout domain, and I will explain, of course, what it is. And then there are other properties which I will explain better later. But in any case, one can observe that F has a subring H which has nice properties, and somehow one can suspect that such an H already contains all the information over the sums of squares, let's say, over the sums of two squares. And in fact, it turns out that this is enough. Having the existence of a subring with several properties, so a Bézout domain with several properties, is enough to show that the Pythagoras number of a function field in one variable over such a field is at most 3. Okay, so I'm finally ready to start describing this method that arises from this observation. So I will fix a field F. Let's say with characteristic different from 2, even though it's not really crucial on most things I'm doing, but in any case I'm not interested in fields of characteristic 2. Good, so I need to give you a couple of definitions and notations. Let's consider a subring H of F. We introduce a new number associated to H, which is the smallest integer, such that any element, any sum of squares in the field that is a unit that belongs to H and is invertible in H. So we are taking the smallest integer such that any sum of squares that is a unit in H is actually a sum of n squares in H. So again, this there is no reason why this such an integer should exist, so it might be infinite. Okay, we haven't given a name to this yet, but P star is enough. I need a couple of notations. Yes, sorry, please. Yeah, I was wondering whether I should fix H already together with the field, but maybe it's no, maybe no. So let's just say that for a subring H of f with fraction, whose fraction field is the whole f, I'm introducing this P star. And for any subring, any ring, actually H, I will denote by max H, the set of maximal ideals of H. By Jac of H, I will denote the Jacobson radical ideal of H. So this is defined as the intersection of all the maximal ideals of H. But you might also know, well, there are several characterizations of this ideal, and I will write the one that will be very handy to me later. So the Jacobson radical ideal of H is made by all the elements of H such that x times any element of H minus 1 is invertible. Good. And last thing I need, hopefully, is a name for this weird set given by all the elements in the Jacobson radical ideal that can be written as 1 plus a sum of squares in F. Sorry? Yeah, thanks. Okay, I know this looks weird, but you will see immediately why I introduce it. Okay, I guess also P star should look a bit weird to you, but I introduce it because with those two things I can formulate this theorem. So assume that we have a subfield, a subring H of F whose fraction field is the whole F. If any non-zero sum of squares can be written as a square times an element of that weird set there, then the Pythagoras number of f is bounded by this other weird constant P star plus 1. Lift. Okay. So it's actually pretty easy to prove it. So consider one element, let's call it F, which is a sum of squares. So by this hypothesis, so there exists, sorry, maybe I should give a name first. let's call P this P star. But okay, let's take an arbitrary element, an arbitrary non-zero sum of squares. We want to show that this is a sum of P plus 1 squares, right? That's what it means. What it means. So we can apply our hypothesis. So we can take an element in F and another element in H, such that F, let's call it G, such that F is C squared times G. So let's look at G. So G is in MH. So it's, we are putting it in a very specific set. So in particular, since G is in M of H, so it's in the Jacobson radical. So this element is invertible in H, right? So it's just 4, of course, here's 1 plus 1 plus 1 plus 1, so belongs to H. So 4 times G minus 1 is invertible. And moreover, we have that 4G minus 1 belongs to 1 plus the sums of squares. So sorry, G belongs to 1 plus the sums of squares in F, right? So 4 times G minus 1 belongs to 4 plus 4 sums of squares minus 1. Now this is again in the sums of squares, right? And this is free. So this is in 3 plus the sums of squares, which are sums of squares, right? 3 is 1 plus 1 plus 1. It's a sum of squares. Okay, you're wondering why am I looking at 4G minus 1? Because now I can look at this element. So what is this? This can be written as 4f divided by 4 f is c squared g, right? So I can collect this one and obtain this equality, right? But so this is a square times an element which is a sum of squares and invertible in H. Okay. But let's look at this definition. So P is the smallest integer for which this inclusion holds. So it means that this thing here is contained in the sums of P squared, right? So of course the square doesn't affect this inclusion. So now f will be c squared divided c half squared plus a sum of p squares. So f belongs to the sum of p plus 1 squares in f, right? So the Pythagoras number of f is at most p plus 1. Okay, so okay, it's you might argue it's there's a trick to use that you wouldn't think about it. That's true. It's not trivial to find the trick, but once you found it, it's just real easy algebra. Good. So you see, I managed to give a bound on f, provided I can find a very nice h. But okay. First of all, in order to have a concrete bound, I must be able to compute p star. So it's already something. But let's assume that we are able to do this. But even then, I still have to show that any non-zero sum of squares can be rewritten as a square times an element which is in the Jacobson radical n that can be written as 1 plus a sum of squares. So you see it's a strong hypothesis and quite a weird one, so it's not easy to check. So I will try to find an example, let's say, of a subring of f where this holds, and I will try in particular to show step by step how to make this hypothesis more nicer, let's say. So I will give you a couple more definitions. Right. So, okay, a ring is semilocal if it has finitely many maximal ideals. Only finitely many. And I promised to talk about Bézout domains. So, a Bézout domain is an integral domain whose finitely generated ideals are principal. So if an ideal is finitely generated, then it must be generated by one element. So it's similar to a PID somehow, except that it might be non-material. So this is the kind of ring I want. But actually I want a bit more. So a subring H of F such that the fraction field of H is the whole field is called a square effective subring of F if for any k positive integer and for any f1 up to fk elements in the field, we have that there exist g1 and gk in f such that the sum of squares of the fi's is equal to the sum of squares of the gi's. And if we take the finitely generated submodule generated by submodule of f generated by the fi's, this is principal, and in particular generated by one of these gi's, so let's say Q1. And we also assume that all of the gi's are in G1. Okay, this I agree is as weird as the other ones, but what I'm asking to such subring is that any sum of squares can be rewritten as a sum of squares, but with other elements, such that the one of these elements generate the submodule, the H submodule of R of F, generated by the Fi's, and I'm also assuming that GI is contained in this. Okay, so the fact is, what you should get from this definition is that in F, if F is the fraction field of such a subring, then I can take an arbitrary sum of squares and rewrite it in a better way. So I find a better representation of these squares. More specifically, are there any questions? Okay, so let me say in words in the meanwhile, so you can check from the definition of square effective subring, you see immediately that square effective subring is a Bézout domain, right? Because take elements in H. I'm saying that any finitely generated ideal of H is actually principal. So H square effective implies H Bézout, and moreover it has this nice property that any sum of squares can be written as a square times 1 plus a sum of squares in H. So again, I can find a new representation like this, and if I look at G1, I can collect G1. So this is the G1 squared times 1 plus G2 divided by G1 squared, GK, G2, G1 squared, right? And these elements are in H, so G1, GI divided by GA, G1 is in H for F4, right? So we have this basically. And this is good because it allows me to show the following proposition. Okay, no, actually I won't prove this, but so if I have a subring with the following properties, so you got that I want to talk about subrings whose fraction field is the whole F. If H is a Bézout domain, and if 1 plus the sums of squares are invertible, then H is square effective. Okay, this is actually very easy to prove. How easy it is. So I leave it as a homework for next seminar. But okay, it's really just computational. There is nothing smart. Let me just mention this condition here means morally that if you take a maximal ideal of H and you quotient H modulo this maximal ideal, it's a field, and this condition imposes on the field that the level is not 1. But okay, let's move on. So I will use this proposition to show the following. So remember, I'm trying to make the conditions in theorem 1 more approachable. So if H is a square effective subring of F, and this weird set M is non-empty, then the Pythagoras number of the field is at most T star of H plus 1. So you can see before I was showing that all sums of squares are in square times MH. Now I just check that I just have to show that MH is non-empty, which is already better, and that H has nice properties. So we can consider an element in an H, and we can look at its square. Its square is is the definition still there? Yeah. So you can see the square will be again 1 plus the sum of squares, because you have things like this will again be 1 plus a sum of squares, right? So it's again in here, and of course it's again in the Jacobson radical, right? It's an ideal. So this square is again in an H, and this implies that any square can be written as a square times an element in MH. So note that this is not trivial, because in general this set doesn't contain 1, because it's a subset of the Jacobson radical, so certainly it doesn't contain 1. Okay, but now we can multiply by 1 plus the sums of squares in H. Okay, so this thing here is again M squared, M and H, right? Because it's again 1 plus the sum of squares. This thing is in H, and this was in the Jacobson radical, so no problem. And this is all the sums of squares by the remark. I guess. Okay, here of course, if I include the 0, I should put 0 also on the left side. Okay, so by theorem 1, we get that the Pythagoras number is bounded by our P star H plus 1.
Can this element G be 0?
The element. Okay, sorry, I forgot. This was going to happen. So no, I don't want it to be 0, which is why I should have defined this set as all those elements, but not 0.
Now that you anyway said that F, you think of F to be a real field, and then Z is not in
I didn't say real. Okay, I should have said real at the beginning and avoid these problems, but okay, you see, if F is real, then 0 does not belong to this set, so no problem. But I don't really need to assume that F is real. Actually, I don't even think I need a characteristic 2, but okay. So you see, if it's real, if it's not real, then this contains 0. And if this is 0, then I cannot show this implication, because here I'm writing an arbitrary square as so f, little f, as f squared divided by g squared times g squared. So if it's 0, I cannot use it. So let's say let's define it for let's exclude 0 from that set. Good. So in any case, it's slowly the hypotheses are slowly becoming better. Let me give you one last definition. So let k be an integer bigger than 2, bigger or equal than 2. We say that f is k effective if there exists a subring f, h of f, such that f is the fraction field of h, usual, h is semilocal, h is the Bézout domain. Then I want that p star of h is at most k. And finally, that the level of any residue field of h is exactly k. So if I have these 5 conditions, I call my field f on some subring of f. I call my field f k effective. So let me write the statement first. So let again k be an integer bigger or equal than 2. If f is k effective, then the Pythagoras number of f is at most k plus 1. So let me make a couple of remarks. So I was starting from that weird condition that we don't know exactly how to tackle. So, that any sum of squares can be rewritten as a square times an element in this h. And now I'm assuming that there exists a subring with these conditions, and these conditions are much more normal somehow. So semilocal, Bézout domains, they are all very well-known concept in algebra. And the level of residue field is also not nothing too weird. I'm still assuming this because, as I was saying, one thing at a time. So let's first remove this, try to make this first hypothesis better, so in this way. I think I don't have the time to prove this, but it's you can really try to do it on your own, just putting all the pieces together. So you will have to take H with these properties, you apply the proposition, then you apply theorem 2, and just check that all the hypotheses work. Okay. Let me just conclude in the last 2 minutes. Let's go back to the example of an algebraic function field over an iterated field of formal power series. So in this field, there exists a local global principle due to Colloquium, Parimada, and Suresh. So there exists a local global principle. By these 3 authors in 2009, which allows us to prove after some computation that there exists a finite number of valuation rings on R on F of F, with residue field of level 2, such that if I take maybe I can if I call H the intersection of these finitely many valuation rings, then the sums of squares in F that are invertible in this field are actually sums of 2 squares in F. And the fact is that a finite for a subring H with fraction field the whole F, it's equivalent to be semilocal and Bézout, and to be an intersection of finitely many valuation rings. Intersection of finitely many valuation rings of F. So you will see that this H is a semilocal Bézout domain, and of course it's also the fraction field is the whole field. And this condition will show that our H is 2, P star of H is equals 2. And the condition on the level that I wrote here, it's easy to show that it implies that any maximal area of H produces a residue field of level exactly 2. So we'll have also the 5th condition for A equal to 2. So our theorem 3 will show that the Pythagoras number of f is at most 2 plus 1, which is 3. Good. I stop here.